Okay, logic and truth tables. My high-res slides again, very complicated. So logic, sometimes this topic is referred to as logic, and sometimes Boolean logic, and sometimes Boolean algebra. All of those terms refer to what we're going to talk about today. So Boolean algebra or Boolean logic or logic is a branch of mathematics that involves true and false values. That's what we're going to talk about, true and false values. So typically we see true denoted with a capital T or with a 1, and false denoted with a capital F or a 0. We use Boolean algebra to break down complex problems or statements into digestible logical formulas. And why do we do that? Well, as developers we do that so we can write programs. So we have to be able to express a problem that we're trying to solve or something that we're trying to create in these small little pieces, right, that we can maybe first write pseudocode for and then turn that into code with control flow syntax. So we'll have if statements and switch statements and loops, and these things require us to be able to break down a problem into something we can express in these conditionals and loops and so forth. So that's how we use Boolean algebra or logic as computer programmers or software engineers or developers. And so this is really relevant for us. And we've already been doing it, okay? But we're going to put some formal terminology around what we're doing, and there'll be some things that you learn today too. So let's talk about some Boolean operators, and then we're going to go into detail about these operators. So first we have unary operators, which are just operators that operate on a single proposition, okay? So we have one called identity, which just says that true is true and false is false, okay? That's all identity means. True is true and false is false. Negation is if we have the opposite of true, if we have not true, that's false. And if we have not false, that's true. So these are really like obvious things that I'm saying, right? But when we want to break down problems and express them formally with logical statements, we have to put very specific terminology and distinctions around these things, okay? So that's all that we're doing here. All right, so the unary operators are pretty straightforward, pretty simple. And then we have binary operators. So binary operators mean that we have two propositions, okay? Two statements. A proposition is just a statement, something that can be true or false when we're talking about logic. A proposition is something that can either be true or false. So with binary operators we have two statements, and each statement is either true or false. So these statements can be expressed as a Boolean value, okay? So we have the binary operator AND. AND means that in order for AND to be true, both propositions have to be true. Both statements have to be true in order for AND to be true, okay? We have not AND or NAND. Not AND is the negation of AND, okay? So if we have two statements and the AND operator applied to these two statements is true, then the not AND operator applied to these statements would be false. It's the opposite. We get the opposite result. We have OR. OR means that at least one of the propositions is true, or the statements. At least one of the statements is true. They could both be true, but at least one is true in order for the operator OR, putting them together with OR, to be true. And then we have the opposite of that, the negation of that, not OR. So with not or nor, we get the opposite result that we do when we apply OR between these two statements. And then we have exclusive OR. Exclusive OR is the one that trips people up. Exclusive OR means that exactly one of these statements or propositions is true. Exactly one. One or the other, but not both. Another way to think about that is that they have the opposite Boolean values. We have a true and a false, or a false and a true. If they're both true or they're both false, then exclusive OR combination would be false. Okay? We're going to look at each one of these in some more detail. Now, We also have a different kind of Boolean operator called a conditional, and there are two of these. These are if-then type operators. Okay, one is called implication. Implication says that if P is true, then Q is true. In other words, P implies Q. If P is true, Q is true. The other one is called equality, which says that Q is true if and only if P is true. Now these two have a subtle difference, and I'm going to talk some more about those in some later slides. Okay, there is a subtle difference between these two conditional operators. All right, so let's talk about exclusive or, because exclusive or is the one that trips people up. Exclusive or could be written as, we have a proposition P and a proposition Q. Exclusive or is true when P or Q is true, but not P and Q. So really the easiest way to think about this, though, is that they have the opposite Boolean values. That is I think the simplest way to think about it. They have the opposite Boolean values. In order for exclusive or to be true, they have to have opposite values. One's true and one's false. If both are true or both are false, then exclusive or is not true. All right? Exclusive or can only be true if only one or the other. Okay. We'll get back to exclusive or again. I put it in there a couple of times because it's the one that people always get questions wrong about. So, let's look at some symbology, because this is one of the things that catches people too, is understanding the notation. So we typically see letters used to represent the propositions or statements when we see statements of logic or Boolean algebra. And it's pretty common in textbooks to see P and Q. I don't know why. I'm sure there's a reason. There's probably some Latin words or something that go with those. I don't know. But if you look in textbooks, if you take a logic course, you'll see P and Q. They always talk about P and Q. I don't know who these guys are. But we're going to use P and Q in these slides because that's what you're likely to see out in the wild, is P and Q. So those just are symbols that represent some statements that evaluate to either true or false on their own. Okay? So in Boolean algebra and logic, we're always talking about statements that evaluate to true or false. Okay? So not strings or numbers or anything else. We're talking about Booleans. And then we have symbols in different disciplines. This is the really fun part. For and, for example, there are a bunch of different symbols that mean and it depends on which discipline we're looking at. So I'm going to expose you to some of these symbols today, and you'll see some of these symbols in the quizzes and on the exam. Okay, so we just have to get familiar with them. So some examples of symbols for not, the unary operator not, the negation of a Boolean operator. You might see that weird looking little, I don't know what that's called, little horizontal line, or it's like the edge of a rectangle or something. I don't know what that is. Little corner. It's probably called something. I don't know what it's called. But that's a common symbol for not. The tilde is also a common symbol for not. Another thing you might see is a line drawn over something. So for example, I might have something like P and not P, like that, with a line over it. That also can mean not. So for not, I can have, let me take it off of there. For not, I could have it like that, I could have it like this, I could have it like this. Sometimes it might look like that. So there are a lot of different symbols for not. And so when we're looking at logic textbooks, usually and looks like that upside down V, the caret symbol. But what are some other ways we see and? What are some other representations of and? Ampersand. So we have a single ampersand for a a bitwise and we have a double ampersand for a conditional and, like for the when we're trying to get the result of applying a binary operator to two Boolean statements. We use a double ampersand in programming, right? Like if this and that, we use a double ampersand. A single ampersand is a bitwise and, which we'll talk about in a little bit. So I remember that one is and the opposite one is or, because the one that's and is like an A. It's like an A, right? It's like a capital A without the line. So that's how I remember that one is and the opposite one that looks like a V is or. Okay? So there's the line over for not and, right? That's like I was just talking about the symbols for not. And then for nor. So nor is just the or symbol with the line over it, right? So that's the typical symbols when we're looking at logic textbooks. Exclusive or. Have you guys seen this exclusive or symbol before? It's like the crosshair. It's like a circle with a plus sign in it. So that's a typical symbol for exclusive or. Okay? Implies. The typical symbol for implies is an equals with a greater than. And for equality, we call that the spaceship. Have you heard that before? The spaceship operator is an operator that's it's in Ruby, isn't it? Ruby has a spaceship. So, but that's also the symbol that represents the equality conditional operator in logic. Okay. So here's some of the symbols, and you want to be familiar with those symbols because they'll show up on quizzes and on the exam. And if you happen to, have a pastime of reading logic textbooks, you'll see them there too. All right, so how many people have seen truth tables before? Truth tables? Yeah, some people have seen truth tables. So a truth table is just a kind of concise way for us to express the results of Boolean operations. Okay, so in the first table that we have on this screen, we have a unary operator identity, the unary operator identity, which just says that true is true and false is false. For a unary, for the identity truth table, it's really simple. It looks like non-purposeful, doesn't it? Like, why would you need that? Okay, but it just is, it's the simplest Boolean operator, identity. For the negation operator, we need to introduce a second column to our truth table because we have one column to represent the value of our statement, or proposition P, and then we have another column to represent the result of applying the not operator, the negation operator, to P. So we see that when P is true, not P is false. And when P is false, not P is true. That's pretty straightforward, right? Okay, so let's look at some binary operators. And in each of these slides, I'm going to show you the truth table, and I'm going to show you the Venn diagram. Because for some people, the Venn diagram helps it to make sense, and for some people, the truth table helps it to make more sense. So I'm going to show both, and if one of them makes it confusing for you, then you can focus on the other one, okay, to understand the concept. But in the Venn diagrams, the red area, the shaded area, is what represents the result of applying that operator. Okay, so in the Venn diagram also, what's in the circle labeled P are the values for which P is true, or the cases for which P is true. It's where P is true, okay? And the Q is where Q is true. So for and, P and Q are true where both P and Q are true, where they overlap, okay? If we look at the truth table, the way that we write a truth table is when we have a binary operator, or we have two things we're comparing, we put P in the first column and we put Q in the second column, and it's a convention to write P as true, true, false, false, and then Q is true, false, true, false. All we're doing is getting all the possible combinations of P and Q. So in the first row, P is true and Q is true. In the second row, P is true and Q is false. In the third row, P is false and Q is true, and in the fourth row, they're both false. So can you see we're just showing all the combinations? The conventional way to do that is to write for the P column true, true, false, false, and for the Q column true, false, true, false. Okay, so when you're writing truth tables yourself, just write those two columns just like that. Okay? Then when we get to the column that's expressing our operation, we look for that row at the values of P and Q, and we apply the operator. Okay? So in this case, we're applying the AND operator. So we look at the first row. In the first row, P is true and Q is true. When those two propositions are true, then the result of AND is true, because AND is only true when both propositions are true. Okay? So in every other case, AND is false. If P is true and Q is false, AND is false. If P is false and Q is true, AND is false. If they're both false, AND is false. They must both be true in order for AND to be true. Does that make sense? Okay? So that's AND. AND requires both to be true. Not AND is the opposite. It is just the opposite. So when I want to represent a not AND, I make a truth table with an extra column. So first I work out what AND is. We already know that. So AND is this third column, right? Where it's only true where P and Q are both true. And then I just look at this third column. I ignore the first two. I only look at the third column and I write the opposite. That's all I'm doing. Okay? So if there's a true here, I write not true there, which is false. If there's a false here, I write the opposite. Okay? So that's how I do not operators. Okay? And if we look at the Venn diagram, it's just the opposite of what we see with AND. Instead of only what's in common being true, it's everything that's not common is where we're true with a not AND. Okay? So far so good? It's all right? All right, OR. For OR to be true, we just need at least one of them to be true. P or Q must be true. They can both be true. So that's why we have the whole P circle shaded and the whole Q circle shaded, including the place where they overlap. Okay? Because OR just says at least one of these is true. So in the truth table, we start with our P and Q like we do for every truth table. And then for the OR case, we look at each row. True or true is true. True or false is also true. False or true is also true. The only case where OR is false is when both are false. Okay, does that make sense? And guess what NOR is? Not OR. It's the exact opposite. So I make a fourth column. In the third column I do P or Q, which we just went over. In the fourth column, I just take the opposite. I take the negation. So where I have a true, I put a false. And where I have a false, I put a true. And the Venn diagram looks like the opposite. Okay? Exclusive OR. So exclusive OR, what is exclusive OR? How did I say it? Like, how do we say it in English? What's exclusive OR? That's right. One or the other, but not both. One or the other, but not both. Another way to say it is that the values are opposite. The values have to be opposite. They can't be the same. The values must be different. So exclusive OR is only true where we have a true and a false. You know, either P is true and Q is false, or P is false and Q is true. What that looks like in the Venn diagram is everywhere in each circle except where they overlap. Okay? All right, so those are the binary operators. Do those feel okay so far? All right, you just have to memorize what they mean, you know? And you can just practice writing the truth tables and make sure that it's clear to you, that you understand, you remember which one's which. All right, so let's talk about implication and equality. These are a bit weird. There's a very subtle difference between them. So I'm going to try to say it in a few different ways. So implication is expressed with the equals greater than. So P equals greater than Q. That's how it's expressed symbolically, okay? The way we read that is P implies Q, or if P, then Q. That's two different ways to kind of say that in English, what we're representing there, okay? What it means is, if P is true, Q must be true in order for the implication to be evaluated to true, okay? For the implication to evaluate to true, if P is true, Q must also be true. If P is false, we don't care about Q. Q could be true or false, and the implication's still true. The only thing we care about is if P is true, Q must be true. So the only case that implication is false is when P is true, and what is Q? The only case where implication's false, evaluates to false. P is true, and Q is false. Because we're saying, if P is true, Q better be true, okay? And if it's not, then the implication's false. Then P does not imply Q. If P is true and Q can be false, then P does not imply Q. All right? Now, differentiated from that is equality. Equality is expressed with the spaceship, or the double-sided arrow, and it reads, Q can only be true if P is true, or Q if and only if P. Okay? So it means if P is true, Q must also be true. And if P is false, Q must also be false. So it's the equality operator. They must be equal, in other words. Okay? Is the simple way to say it in English. So if P is true and Q is false, then equality is false. If P is false and Q is true, then the equality is false. Okay? So they're not the same. People get confused and think that implication is the same as equality. Okay? But that they're not the same. So let's look at the truth tables. So implication is the one that trips people up. Equality is pretty straightforward. They have to be the same, right? That's pretty straightforward. But implication's a bit tricky. So probably the easiest way to think about implication is just to remember that the only case that it's false is when P is true and Q is false. That's the only case that implication is false. In every other case, P does imply Q. We can say P implies Q. People get tripped up when P is false and Q is true. They get confused about that. They're like, well, that means that P doesn't imply Q. No, it doesn't. It means that Q doesn't imply P, but it doesn't mean that P doesn't imply Q. P can be false and Q can be true, and we can still say that P implies Q. Okay? Because P implies Q is only a statement about when P is true. Okay? All right? So if you can just sort of remember that the only case that it's false, then you'll be okay. Okay? So the second truth table is another way of thinking about P implies Q, because P implies Q is the same as not P or Q. That's not helpful to some people, but for some people it is. So if we write out not P or Q in the truth table for that, we get the same result. It's another way of thinking about it. But I think it's probably simpler just, to consider the only case that it's false. Equality, pretty straightforward, I think. Okay? The problem just gets to be in confusing implication with equality. But equality is they have to be the same in order for equality to be true. All right? You can also think of it as the opposite of exclusive or, right? they have to be the same instead of they have to be different. Exclusive OR is they have to be different, right? And equality is they have to be the same. All right. So far, okay? Okay. Let's talk about bitwise operations. So we can combine binary values. Binary values are just numbers expressed with the 2-digit binary number system, right? Zeros and ones. So we can combine binary values using bitwise logical operations. Okay? It's less complicated than it sounds. It sounds complicated. Bitwise logical operations. You're like, oh my God, what is that? So if we have two binary numbers, they have to be the same length. So if they're not the same length, then we fill in with zeros on the left. So we don't change the value of the number, but we need to have the same number of digits in order to do bitwise operations. Okay? We just consider each position individually. That's all we do. And we perform whatever operation, an AND or an OR or an exclusive OR, on each set of 2 bits. Okay? So let's look at some examples. So if we have, for example, 110011 and 101100. Now, on a quiz, these could be represented in hex, and we have to change it to binary first in that case, okay? Because we're doing bitwise operations, which implies that we're dealing with binary numbers, all right, true and false. So you might see it written as this way with the and in the middle, but more likely you'll see it written with a single ampersand. A single ampersand means bitwise and. A single pipe means bitwise or, okay? So all we do is we write out the numbers like I have written here, okay? So where P represents the first number, 110011, and Q represents the second number, 101100. And then we just take those values one at a time in columns, and we apply AND in this case because it's a bitwise AND. So if we look at the first column, 1 and 1 is 1. Yes? True and true is true. The second column, why is it 0? Because we have a 1 and a 0, and that's false. That's 0. So where's the only time we get a 1 as an answer in a bitwise AND? What's necessary for us to get a 1? They have to both be 1. They have to both be 1 because this is AND. Okay? So we get 1, a 0 in the second column because we have a 0 there, right, for Q. We get a 0 in the third, or sorry, we have a 0 for Q. The third column we get a 0 because we have a 0 for P. The fourth column we get a 0 because we have a 0 for P again. The fifth one we have a 0 because there's a 0 for Q. And the last one we have a 0. We only have a 1 in the first position because that's the only place where P and Q are both 1. Okay? So the result of this bitwise AND is 100000, which we could express as hex or as a decimal number if we wanted to. Okay? But this is a bitwise AND. A bitwise AND. So we consider one bit at a time and we perform an AND Boolean operation on those bits. Does that make sense?
3 zeros would make a 1.
No, because AND. So you have to go back to the truth table for AND, the understanding of AND. AND is only 1 when P and Q are both 1. Okay? What about OR? When is OR 1? When do we get a 1 for OR?
Either one is a 1?
Yeah, and they could both be.
Oh, yeah.
They could both be. So at least 1, right? At least one of them is 1. So if we have the same numbers, we get 1s all the way across. Because for each position, at least one of them is 1. Does that make sense? So in the first column, they're both 1. In the second column, P is 1. In the third column, Q is 1. In the fourth column, Q is 1. and in the fifth and sixth P are 1. So in every case we have a 1 in at least one of those. So that means that or is 1 all the way across. Does that make sense? What about nor? What is nor again? Not or. So what do you think our answer is going to be if or was all 1s? What do you think nor is? All 0s. It's just the opposite of or. That's all it is. So we work out what or is, and then we take the opposite for each position.
So how do you get a 1 then?
No, for nor we don't.
Ever.
Not for these two numbers.
But
If we had two other numbers, we might get something other than that, right? So if we have two other numbers and in some position we have a 0 for or, like if we had if we had 1 0 0 0 and 1 0 1 0, right? If we did an or of those, what would we get? What's in the first one? 1. What's the second one? 0. What's the third one? 1. What's the fourth one? 0. So what would not or be? The opposite. Okay? So for any of the negations, nor, and, work out the non-negated version first, and then just take the opposite. Okay? Okay, exclusive or. Exclusive or. So what is the rule for exclusive or again? When are we going to get a 1? When they're different. So when we have a 0 for one and a 1 for the other. If we have a 1 for both, what do we get? 0. If we have a 0 for both, what do we get? 0. They have to be different. So for exclusive or, everywhere that they're different, we get a 1. Okay? All right, now, let's talk about adding binary numbers. Adding binary numbers is like adding any other number. Okay? We just have to remember that we only have 2 digits in binary. Okay? But we follow the same process of adding and carrying where we have to. This is different from a Boolean and or a Boolean or. It's not a Boolean operation. But I want to talk about it here because if you see a plus sign, what it means is to add these numbers. We're adding them. We're not performing a Boolean bitwise operation. Okay? So let's add these numbers together. If we have 1 plus 1, what do we get in binary? What do we get in decimal? What's 1 plus 1? 2. What does that look like in binary? 1 0. So we have to put a 0 there, and what do we do with the 1? Carry it to the next place. And then what do we have? 2 again. 1 0. So we put a 0, and we carry the 1. Now what do we have? 3. What's 3 in binary? 1 1. So what am I going to write underneath? A 1, carry the 1. Yeah? And then what do I have? Just 1. Okay, what about the next one? Just 0. Yeah? Next one? Just 0. The next one? Just 1. The next one? Just 1. Okay? If we had to carry in this leftmost place, then we would just end up with an extra place. Just like if we're adding decimal numbers. It's exactly the same. Okay? except that we're only ever in each place going to end up with 0, 1, 2, or 3. Right? So I think there's one like this on the quiz. One of the quizzes next week or the week after. I can't remember. All right? So I actually don't have any binary addition in worksheets, so I'll find one so you can practice. But it's not too much of a stretch, hopefully. It's like addition, but with really simple numbers, you know? Okay, so let's look at some more complicated truth tables where we have more than one Boolean operation in the statement. So somebody tell me what this statement says. Mm-hmm. Yeah. So what do I have to evaluate first? Because we do have an order of operations that we have to adhere to here too. Brackets first. So P and Q, the result of that, we OR with not P, right? Is what this says. All right? So if I'm making a truth table for this, I'm going to create a column for P and Q. I'm going to create a column for not P. Okay? And then I'm going to do the final calculation. So whenever you have multiple Boolean operations in a statement, just make multiple columns in your truth table. Okay? Make it really simple. So the first column, all I'm worried about is P and Q. So what is in that first column, P and Q? What goes there? True, and what's the rest of the rows for the first column? True, false, false, false. Everybody agree with that? Because P and Q. Only true when both are true. Okay? First column, true, false, false, false. That second column, all I'm looking at is P, and then writing not P. So I'm ignoring the two next columns right now to figure out not P. Not P doesn't care about Q, and it doesn't care about P and Q. Not P only cares about P. Okay? So if I just look at P, what goes in the not P column? False, false, true, true. Everybody agree with that? All right. False, false, true, true. Now, for the last column, which two columns do I care about for this Boolean operation? The last two columns, because I'm ORing P and Q, the result of that, and not P. So now all I'm doing is applying OR to those last two columns. That's all I'm doing. Okay? I'm not thinking about the other columns or the other things I've done. I'm only ORing those last two columns. So what do I get when I OR those last two columns? True, false, true, true. Everybody agree with that? Because what is the rule for OR? One or the other or both, at least one. At least one of them must be true. Okay? So for the last column, I only look at those previous two columns to work out the last column. True, false, true, true. Does that make sense? Okay, so let's practice turning some English statements into logical statements with symbols that we know. So if there's smoke, which we're going to represent that statement, there is smoke, that's true or false. There's smoke or there's not smoke, right? And we're representing that proposition, there is smoke, with the letter S. And then there's fire. So we're representing the proposition there is fire, which is true or false, right? With the letter F. So if we have the statement, if there's smoke, then there's fire, what is that? How would you represent that with symbols? What is that? What kind of relationship is that?
Implication.
It's an implication. Yep. So how would we write it? Yep, what goes on the left side of that? S. So it would be S implies F is one way we could say that, right? S implies F. S equals greater than F, right? S implies F, is how we could represent that. Does that make sense to everybody? Okay, so it is raining is represented by R. I am outside is represented by O. I have my umbrella is represented by U. Okay? So if it is raining and I'm outside, then I will have my umbrella. If it's raining and I'm outside, then I will have my umbrella. So we have raining, outside, umbrella. What do I have to write?
Rain and outside.
Raining and outside. I'll put some brackets around that.
And the equals greater than inside.
Implies I have my umbrella. It's raining and I'm outside. Implies I have my umbrella. Okay? Does that make sense? So we don't really need the brackets because it's the only thing on the left-hand side. But anyway. Okay. I wear bunny ears on Twitch is B. I get another subscriber is S. Donation, I get a donation is D. Okay? So I will wear bunny ears on Twitch if I get another subscriber or a donation. So you're saying B implies S or D. Almost. That's right. S or D implies B. So even though the way we say it in the statement, we're saying I will wear bunny ears first. It's really though the I can't think of the word of the implication. There's a word for it. So S or D implies B. Because we could re-say the sentence, if I get another subscriber or a donation, then I will wear bunny ears. Okay?
Is there a reason why the sequence is important, just mathematically, or
Well,
how you write?
so there's a little bit of a trick, and this is always the challenge with programming and with math word problems. It's the same challenge, is being able to hear something in English or express something in English and then turn that into something we're expressing with logic. It's our challenge as a programmer too. When we have to write an application or a function or an algorithm that solves a particular problem, for a lot of people, for most people, the most challenging part of that is this ability to turn that into a logical representation. And what we have here, I will wear bunny ears on Twitch if I get another subscriber or a donation. The way to represent that logically is S or D implies B, not B implies S or D. Those are two different things. If we coded those two things, we would get different results from our application. Okay? So what is really being said here is that getting another subscriber or a donation implies. So those two things, if either of those things are true, then I wear bunny ears. Okay? So if that's the result that we want our application to produce, then we have to code it that way. All right, so it just takes practice. It takes practice in reading and recognizing what's actually being said and turning that into the correct logic statement. And that's, I think, the most challenging thing about programming, more so than learning syntax or semantics or how a particular language or library or framework works. I think this is probably the most challenging part of programming. Okay, so what about I am an admin is A, I'm a teacher is T. So admin or teacher has access, given that whoever it is, the staff member, is not both a teacher and admin. So staff is admin is A, the staff member is a teacher is T. Okay? We can have other kinds of staff members, right? So staff member is an admin is A, staff member is a teacher is T. And the statement is admin or teacher staff have access given that that staff member is not both a teacher and an admin.
Is an exclusive order?
There is an exclusive or in there, yes. So, teacher or admin but not both. So teacher exclusive or admin, yes? And what's the rest of it? Implies access, which we don't have a symbol for in there. Yeah, that's exactly right. Teacher exclusive or admin exclusive or teacher implies access. Okay? So, I don't know if there's anything like this on the test or quiz, but I think it's really, this is the real application of this topic. We have to be able to turn the things we want to express in code into code. And code is all just control flow, right? Representing the data in some way and then controlling the flow of our program with Boolean algebra. That's all we do. That's all we do as programmers. Okay? All right. So that's the end of that lesson. It's 11:12, which is not quite lunchtime, but you probably want a break before we talk about sets. So maybe the thing to do is take from now until lunchtime to do the worksheets, or at least as much as you can, the worksheets for this topic, okay? And then you can have some lunch, and then at 1 o'clock we'll go on with sets. That sound all right? Okay, cool.